so what we talked about last Wednesday, is that right? We started chapter 4. We talked about photons, what photons are, and photons, this was the start of electromagnetic energy. Photons, we discussed what a photon is, and that is kind of like an atom of light. It's the single smallest portion of electromagnetic radiation, right? So that's the kind of the comparison there. We've talked about atoms as kind of like an atom of light. Also, a lot of times referred to as quantum. We talked about the properties of electromagnetic energy and who described those properties, and that was James Clerk Maxwell. We talked about the speed with which all electromagnetic radiation travels, and that is the speed of light, right? So we talked about you can't speed it up, can't do anything aside from put it through a different medium to slow it down. So it's the speed of light in that medium, and it's always going to be constant in that medium, right? So we talked about velocity. Velocity doesn't change. And we talked about amplitude and amplitude of all the different attributes that we were describing. Amplitude was the least significant. That was just quantity of electromagnetic radiation you had, right? So for this portion right now, what we're focusing on is really kind of the power of the electromagnetic radiation. And in that context, the power is equivalent to what we refer to as kVp. So the power, the energy level that we're talking about is power. And that power is not the intensity. Intensity is the numbers, but rather the frequency and the wavelength. So we talked about frequency and wavelength. We talked about all types of electromagnetic radiation travel in waves. So the characteristics of the wave was amplitude, and that was just the quantity of electromagnetic radiation we had. And then we talked about the wavelength and the frequency, and we drew it out. We could have two different waves, one with a wavelength like that, and then one with a wavelength like that, and we determined that wavelength and frequency are inversely proportional. As one goes up, the other goes down. Since these are constant, traveling constantly, if we were to measure how many waves would pass a point, then this would be more frequent, right? And this would be less frequent because this has longer wavelength and this has shorter wavelength. So in comparison they're inversely proportional, frequency and wavelength. When you're comparing the two, they're inversely proportional. We also talked about energy and tied that into frequency. As the frequency goes up, then we also have a higher energy, right? So we looked at our diagram or our table on page 59, and that kind of bears that out. As energy goes up, then frequency goes up and wavelength decreases. Now, while we're on this, I don't want to have to step back to this and have you switch gears. And why Bushong didn't put this into the book in that discussion is if you look on page 66, then what you see is that it's the bottom right-hand box, and it's not a pig one, it just has Bushong's face in it. But it's a mathematical equation that we refer to as Planck's constant. And Planck's constant describes that relationship between frequency and wavelength, or frequency and energy. That energy and frequency kind of follow each other. They're not really one and the same. It's just the higher the energy, the higher the frequency, the higher the frequency, the higher the energy. So again, if we were to simplify that equation, Planck's constant, then we would have 1 equals 1 times 1, where in Planck's constant, what we're looking at is energy. Energy is equal to frequency times wavelength, right? So if we were to increase our frequency, then in order to maintain the same energy, what would have to happen with wavelength? For this, okay, let's do this. 2 times, to keep this at 1, then wavelength would have to,
Half.
yeah, 1/2, right. So really, Planck's constant, you can almost look at it as a rearranging of the wave equation. It's really similar to the wave equation. It just describes, though, how energy and frequency interact, or how they help to describe each other, right? So that's what Planck's constant is. So when you get to that, whenever you're reading through this book, just understand that's what that is it's just describing how energy and frequency, one follows up. Okay. So we didn't mention that in the last lecture, so I just thought I'd throw it in here, just in case you've read through the chapter and got to that point. So another thing that I didn't discuss is that what we refer to in our frequency and how often something travels in a sine wave passes an area or whatever, is we refer to that as hertz. That's a Z, not a 2. It's a hertz. Okay, so like electricity that you get out of the wall is alternating current. It also travels in a sine wave. It goes back and forth, back and forth, back and forth. That's what we refer to as alternating current. Direct current is what you get out of a battery, and it just goes in one direction at a constant rate. Okay. But alternating current goes back and forth, and it cycles. And that's another way that you can refer to it as hertz, is cycles per second. So hertz, or cycles per second, the electricity that we get, and it's not in the textbook until later on, but it's 60 cycles per second is how often our electricity changes direction. So that's not on the test. That's just to try to help you to remember what hertz is, what hertz are. All right. So that'll be on the test later on. All right. So what we determined then was that frequency and wavelength are inversely proportional, and then frequency and energy are directly proportional. The frequency and wavelength, as one goes up, the other goes down. That's why it's inverse. And with energy and frequency, they both go in the same direction. We took a look at the electromagnetic spectrum. We looked at all the examples that Bushong described in the book. We looked at visible light, and visible light on that table populates just a small portion of the table. But we've got a lot of different energies: radio frequency, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. So what we're going to learn is that X-rays and gamma rays are very similar to each other. They can do the same things. Really, the main difference between the two is that gamma rays come from the nucleus of the atom, as opposed to X-rays we create outside of the nucleus, right? Through brims and through characteristic X-rays, they're created in the electron shells. So that's pretty much where we left off. Any questions on that? We also talked about the ultrasound, the energy in ultrasound being sound waves rather than electromagnetic energy. Any questions on all that? Yes.
Sine waves.
Sine waves.
Yeah.
Sine waves, they're just oscillations. Okay, so they travel, and this is something you got to memorize, because I can't demonstrate this at all except for to draw it. But electromagnetic radiation travels in waves like this. So the sine wave is turn this sideways. You turn. See if I can draw this properly. Turn that sideways, and what you have is a sine wave.
So it's just the waves turning sideways.
Well, I just use that for memorization purposes. The sine waves are the waves. Yeah. And it's just oscillations that go back and forth, up and down. Yeah. Anything else? No. Okay. Okay. Then what we're going to talk about today is we're going to follow up with the electromagnetic spectrum and the types of energy that we are most interested in and use in diagnostic radiology. some of which we don't want, and some of which we do want, right? So we're going to talk about the inverse square law, and I'm going to give you kind of a preface to the direct square law, which is identical to the inverse square law, except for the second half of it is inverted. So the inversion portion is inverted, and it's righted. So it's a direct square law instead of the inverse square law. So the types of electromagnetic radiation that Bushong talks about in, let's see, on page 60 and 61, he mentions three different types of electromagnetic radiation. You got visible light. So visible light, we use in a lot of different ways in X-ray. First off, we can't see our X-ray images unless we have visible light, right? We also use visible light in determining where the radiation field is going to be. All right, now again, this is something that we're going to talk about later on, but what you've got, and this is not on this test, construction of the X-ray tube and the X-ray tube housing. What you have, let's cough, I guess bless you. But what you have inside of the tube housing or the protective housing, you've got the X-ray tube inside of there, right? You've got the cathode over here and the anode over here. And then you've got all the components inside the protective housing protect the tube against you and you against the tube. And then beneath that, what we have, kind of drawing it off center here, is the collimator housing. And it's a totally different animal. And whenever you hit the collimator button so that you can see your projected light field, what you're actually doing is energizing a light bulb. Let me draw this bigger than that. What you're doing is you're energizing a light bulb inside of this housing. And that light bulb is shining onto a mirror that is at a perfect 45-degree angle. Mirror that is at a perfect 45-degree angle. So that light field reflects directly down at a 90-degree angle so that you can see where to put the crosshairs and where to put your radiation field. So it's visible light. We use visible light so that we can project a light field to determine where the radiation field, we're going to get real specific about this later on, but we're going to project the light field so that we can see where our radiation field is going to be. All right, so if you look up inside of your collimator housing, you can see that mirror. And in the mirror, you're not going to see yourself because it's a 45-degree angle. You might not even see the light bulb, but it's in there. All right. So sometimes whenever you hear a fan kick on, if your light bulb is an incandescent lights are the lights with the filaments, they get really, really hot. And sometimes when you hear a fan kick on, that fan is to cool that light bulb down and not necessarily the fan to cool the X-ray tube. Okay. So we use visible light to make a diagnosis to see, obviously, and also to project our radiation field. So visible light's a big one. Okay. So that's number one. What else does he have? He's got a radio frequency. All right. So radio frequency, oddly enough, whenever he first wrote this book and this chapter, we almost didn't use radio frequency at all. You might have used it in a radio or maybe a telephone that you would use to call a person who's working on portables to go to a different room and take an X-ray on that portable patient. Now we use it a lot. All right. So when we make an X-ray now, you shoot into the image receptor. And the image receptor sends a radio signal. Like if you got lab today, look over the sink. Okay. So if you look over the sink, almost to the ceiling, you got this box sticking out. It's got an antenna. That antenna is what they refer to as a dongle. D-O-N-G-L-E, I think is how you spell that. Who came up with that word? I have no clue. But it's a dongle. So when you make an exposure, the image receptor receives that information and it sends a signal over to the dongle, and that translates the signal over the computer. So those are radio frequency waves that send those. If you're working on a portable, same thing. You've got, unless it's a tethered image receptor, you've got radio frequency that are sending a signal for the captured image to the portable to create that image for you. Okay, so we use radio frequency a lot more now than what we used to. So radio frequency. And then certainly we use ionizing radiation. That's what we're hoping to get out of the X-ray tube, right? In the form of X-rays. Right, so the X-rays are ionizing radiation. They come out, and that's what exposes your image receptor. But what's the main thing that we create inside of the X-ray tube? Heat. So infrared radiation is the main thing that we're going to deal with. And oddly enough, he didn't include it. I think probably because we don't use the heat, but we got to deal with the heat. So we have to acknowledge that it's there as something that we're going to have to deal with. So how did we deal with the heat? 3 ways?
Conduction,
A lot of y'all are answering. I can't understand what you're saying. All I got was in and yeah, conduction, convection, and thermal radiation, right? So we conduct the heat all across that great big chunk of metal, and then we thermally radiate it to the glass, and then we conduct it into the oil, and then we have fans that blow across and convect the heat and try to remove some of that heat, right? So we deal with the heat in those 3 different ways, and that's the main thing that we create. We do create a little bit of light if you ever. I've got some videos that a biomed guy took and sent to me, and he was working on the machine with collimator housing off, and he took some images that showed the electrons jumping from cathode to anode, which is, it sounds like it's pretty cool. It's really, I guess it's cool to see once, but all you saw was this flash, right? So there is a flash. If your patient ever says, I know it took because I saw the flash. They didn't see any flash. There's a flash. They didn't see it because the collimator housing, blocks it all off. But there is a flash. When the electrons jump from cathode to anode, you do see a little flash. Okay. So there's light. We do create light in the X-ray tube, but you can't see it. The main light that we're interested in seeing is invisible light, and that is your ionizing radiation or your X-rays. Okay. Any questions on that? Okay, so I'll warn you, this is a little bit conceptual. I'm going to kind of fast forward through these. These are the videos that are posted into Canvas. No penalties. Anybody get a chance to see them? Watch them? Take the chance to see them? Okay, good. Then I'm not going to bore you with something that you've already seen. I'm going to bore you with something that you haven't seen. All right, so electromagnetic radiation has a dual property. Right, so sometimes it behaves like particles, sometimes it behaves like pure energy. And what we're going to look at is what we refer to as the double slit experiment. And I've seen this in person. It's really pretty cool. It's cooler in person than what you see here. And they always come up to a point and leave off a point that I think is very important. I'll describe it to you here in a minute. But this guy created this great big box, and he took it down to the beach and was trying to show people how it is that light are waves, or light is waves. So I'm going to fast forward through a portion of this. He's got this great big box, and what he's got.
What is light? Light was the whole.
Let me silence it for a minute. But what he's got is he's got this great big box, and he's got this thing that you can see inside of the box, right? And then he's got an area where he's got 2 slits in something that's very opaque. Like maybe you took a a lab slide, painted it completely black, and then, has two slits that are really, really close together, almost imperceptible. So light can get in through those two slits, and what he wants people to do is look inside this box to see what happens with that light that's projected through those two slits. Okay, so
That's a good question. What is light?
but he starts with this. What is the same question I asked y'all last time? What is light? And they have the same answer. Light is light. I don't know.
Light is brightness, I guess. Yeah, Morris.
They all have a
Is there a light?
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light? The color goes in your eyes, and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, yeah, it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me. To be fair to the question of what light is not an easy one. For centuries, the greatest minds in science debated this
So-
issue. In the late 1600s, Newton.
I'm going to fast forward this and kind of show you his setup. So, what this, in a lot of cases, what they do in the double slit experiment, they start with a single slit. So, they'll project light through a single slit, and the appearance of the light is going to be, pretty specific. And it'd be kind of like how you would expect it to be. It's bright, and then it gets dimmer the further away from the slit it gets. And then they'll introduce the two slits, and that's where the magic happens, is when you have the two slits.
Very narrow opening side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom? Well, all these things, you're thinking you're going to see, you're going to see two lines. Two lines on the bottom of the box. Two bright bands. Yeah.
Yeah, I think it'll be one light and two.
I could expect some whole hospital.
That can be a kaleidoscope, some
A
sort.
bunch of colors.
Probably, yeah.
Alice?
There, have a look. You expect to see kind of one line. Is that what you see?
No,
I see dots.
it's one circle.
Oh, there's one in the middle strong, there's two out the side.
Two on the outside are multicolored, one in the middle is just white.
Kind of a rainbow.
The rainbow color as well.
So a few colors and lots of little dots.
There are more dots appearing.
I think I can see more dots. Spreading along.
So this is what you're seeing. So instead of two vertical lines, like what you would logically think would happen, is that as the light goes through and it interacts with the two slits and then interacts with each other, then what you get is, instead of two lines, you get this interference pattern that gives you decrease in intensity out and away from the center. But instead of two lines, you get a whole lot of little bitty dots. Okay. Now, I'm not going to play all the way through both of these. You've got them. If you're really curious, you can watch all the way to the end of both of them. But this is the experiment that I actually saw. And oddly enough, it was during a philosophy lecture, right? It wasn't even, a science lecture. It was a philosophy lecture. So the guy had red argon light source that he was using, and he had not only double slit, but he had single slit, and he had a double slit where he could slide the slits further and closer to each other, right? So he started off with a single slit, and you would see what you would expect to see if you were shining a light through a crack in a door. You'd see, a line, and then it would get progressively lighter, or less light, darker. And then he brought the second one in, and we got this interference pattern. And again, in this video, and also in the Bushong book, he describes interference patterns, and you can see interference patterns if you're standing still in a swimming pool, We're gonna use water a lot this semester, by the way, especially when we get into electricity. We're gonna use water as something that we can visualize and use as an example of how electricity behaves. But you're standing in a swimming pool and you're perfectly still, and there's no waves emitting from you. If you take your hand and you splash your hand in the water, then you're going to see waves, right? But if you do them both at the same time, then you start to see this interference pattern where the waves are kind of crashing into each other and kind of giving you this thing. So then the question becomes, is light a particle as you would expect it to look like a particle if you shot it through a single slit, or is it a wave like what you would see if you shot it through a double slit? It gets even more complicated in where I was going with the example that I saw, and where it is that they pulled these experiments up just a little bit too soon. Is in the example I saw is if he had the slits close enough together, you would get this interference pattern and you would get the multiple dots. But if he separated them just a little bit more, it would go to not this, but individual slits all over again. So if they were close enough together, you got that. But if they were far enough apart, but they were still wide enough, or still, within the projected light field, then it went back to individual slits. And that was weird, because I could wrap my mind around the first one with a single slit. I could kind of accept this with the interference pattern discussion. But once you spread them out far enough, the interference pattern didn't really matter anymore. It ignored the interference and it went back to two individual slits as if it was a particle. So then the question becomes, what is light all over again? Is it pure energy, or is it individual pieces of things like photons? Is it light, or is it a particle? 3-word answer. I don't know. Who knows? Don't know. Still don't know. Scientific community doesn't know, but what they do know is under certain circumstances, it behaves like a particle. And under other circumstances, it behaves like pure energy. Okay. So double slit experiment makes it appear to be more like pure energy as opposed to, a particle. But then you introduce energy levels and how they interact, right? Or how they behave. So when we make an X-ray, it's getting a little further into the chapter, but when we take an X-ray, what we create in the X-ray tube are X-ray energies of all energy, right? So if we make an X-ray beam that's 100 kVp, we're going to create X-ray photons here effectively at 0 kVp all the way up to 100 kVp. Okay, and we expose the patient to that energy, and once it gets inside of the patient, what's it going to do? Really, fundamentally, 3 things. There's 4, but really in the diagnostic range. When we get into therapy ranges, something totally different. But in the diagnostic range, what's it going to do? Absorb, scatter, or transmit. One of the 3. Right? So it's almost like each individual X-ray photon is on its own to do what it wants to do, what it needs to do inside of the patient's body. All right? When you shine a light on somebody, what happens?
Shadow.
They just get shadowed. It doesn't go through the patient at all. Right? So the whole thing absorbs at the patient's skin level, as opposed to the X-rays. Each individual photon does its own thing. Okay, so in that way, visible light behaves more like energy, as opposed to X-rays behave more like particles. Okay, they both have both characteristics, and that's what the book refers to as wave-particle duality. They both have individual, they have both individual characteristics, but X-rays behave more like particle as opposed to visible light, and the lower energies below X-ray behave more like pure energy. Okay, there's your wave particle duality. And again, it's not it's not imperative that you understand all the nuance to that. Just know that X-rays behave more like a particle, and light behaves more like energy. But there is that wave particle duality. All electromagnetic radiation has both properties. That's the takeaway from that you need to know for the test. And you can, get as deep into the rest of that as you want to. Okay? So what is it you can do with visible light? We've talked about a couple of those things. Why could you not see the flash in the X-ray tube?
This is covered.
Because it's covered, right? It's covered. The X-ray, the light that would be projected out from there gets absorbed by all the stuff in the collimator housing. Can't get through. So we can, visible light, we can absorb or completely block, right? So you can't see through that wall back there, right? You can see the wall, but you can't see through the wall, right? Because it blocks everything. And so we can say that that wall back there is opaque. And we use opaque also improperly sometimes. Sometimes like with shower doors. Shower doors are kind of frosted, and some of your manufacturers call that opaque. It's not really opaque. All right. So opaque means that you block everything. You can't see through the wall. But looking just on either side of the wall, what do you see? Glass doors. On the other side of the hallway, you see windows. And on the other side of that second one, you see trees, you see handrail, you see sidewalk, you see the world outside, right? So light can go through things that are transparent. And in that, the light transmits. Right? So transmit through the air, through the window, through the door. Realistically, glass has to be really clear without any color to it at all to be truly transparent. Sunglasses, are they transparent? You hope not. Right? You hope not. But otherwise, it wouldn't be sunglasses. You want them to block certain wavelengths of light, right? You want them to block certain wavelengths so that, it doesn't damage your eyes. Plus, it darkens so that you can, not have to squint. I've got real sensitive eyes. I wear sunglasses anytime I'm outside, just about. It blocks some of that light. So what we have there then is not transparency, okay? That is what we refer to as attenuation. You can attenuate light, okay? And that would be in things that are translucent. All right, so look up the lights. A little bit bright, right? Can you see the light bulb? No, because you got a diffuser there. Okay, that diffuser, the purpose for the diffuser is try to make the light spread out a little bit more, but you can't see all the way through it. It's not transparent, it's translucent. So there are a lot of different types of translucency. You got your sunglasses, but you also have things like that, right? So you can attenuate it, you can transmit it, you can absorb it, and there are two other things. So we have this here so that you can't see the light that flashes across there. But what's this saying? What did that represent? The thing at a perfect 45-degree angle.
The mirror.
Mirror, right? What does a mirror do? Reflects, right? So if I had a mirror up here in a very intense light and I kind of took it and shined it around the room, what would happen?
It reflects the light.
It reflect, exactly. We can reflect light. Then there's one other thing that we kind of talked about before. Anybody ever gone bow hunt or bow fishing? Oh, one person. All right. Do you shoot at the fish when you go bow fishing? No, because if you shoot at the fish, you're going to miss the fish every single time. Why? Because when the light enters into the water, what's it entering into? Different medium, right? So what happens to the light? Refracts, right? So we can also refract it. That's why whenever you put a straw in a cup, the straw bends, okay? And just in case you're wondering, you got to shoot, I believe it's under the fish, right? It's been a long time. I used to go a lot, but it's been a long time. So you got to shoot under the fish. Otherwise, if you shoot right at the fish, it's going to go over the top of him and you're going to miss him every single time. So visible light, you can do a lot of stuff to it. All right. So a few things here. Have you ever heard of anything in diagnostic radiology referred to as in any way opaque? A word possibly attached to opaque to make it specific to radiology. Somebody say it. Say again. Radiopaque, right? It's radiopaque. So let's get rid of our X-ray tube. We'll go diagnostic X-ray. You can absorb it if it is radiopaque. All right. So what does radiopaque mean? It means it absorbs. Right. So bone is more radiopaque than soft tissue, which is more radiopaque than air. Right. Those are the basic three different types of tissue types. Metal, even more radiopaque than all the other ones combined, really. Okay, so have you ever heard of anything being radioparent? Is that?
Like air.
Well, that's good thinking. But no, air is made of particles. Particles made up of atoms, right? So atoms have nuclei and they also have electrons. So if I were to create an X-ray beam and just send it across the room here, you're going to have some interaction with that, right? It's going to be very, 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 very minimal. And you might not be able to detect how much you're going to lose by the time it gets to the other side of the room. It's going to interact with it. So that's conceptual, but inside the patient's body, let's say, in the diagnostic range, you ever heard of anything that was radioparent? Say again?
Like the sandbag, station.
I'm sorry, I'm still exam bags. Is that what you said?
Sandbag.
Sandbags.
Yeah.
Sandbags are really going to be somewhat radiopaque, maybe somewhat radioparent. So they might absorb some, but might let some through. Do we have any words over here that kind of describe that? Let light through, but absorb light. And what's the word? What's that? Attenuate. Okay. There is no such thing as radioparent. Okay, so I'm going to do this. Radioparent ain't a thing. All right. But what we can have is attenuation. We have to have attenuation. Attenuation means selective absorption. In an X-ray, what causes attenuation is different tissue types. So again, bone being more radiopaque, it's still, it's still radiolucent, but it's more radiopaque than soft tissue. Soft tissue is more radiopaque than air. Okay, so we can attenuate things that are radiolucent, but inside the patient's body, you're always going to have some sort of interaction, some sort of absorption. Selective absorption means radiolucency. All right, so can't reflect it. Populate that over here. Can't refract it. Populate that over here. So we can transmit it. The beam as a whole is not going to transmit completely because we're going to attenuate it. But an X-ray photon might make it all the way through the patient without any kind of interaction. Okay, so don't confuse those two. Individual X-ray photons can make it through without interaction. Doesn't mean that the tissue type is radioapparent because it's going to absorb a whole lot more, right? Okay, so in a beam as a whole, the only thing we can do is either completely block it, we transmit individual photons, but as a whole, the X-ray beam is going to attenuate or it's going to stop completely. So there are two types of interactions, two types of absorption characteristics of X-ray beam. It's either going to go through partially or it's going to be completely absorbed. Okay. Any questions on those? All right. So then if y'all are good with that, when you talk about the inverse square law and its kind of accompanying law, the direct square law. So we'll talk about the inverse square law. I don't know, chapter 1 was it? All right. Inverse square law states that the intensity of electromagnetic radiation, so I'm on page 64, second thing, or first thing. The intensity of electromagnetic radiation is inversely related. Stop there. What does that mean?
One goes up, the other goes down.
One goes up, the other goes down. So you've got an inverse relationship. One goes in one direction, one goes in the opposite direction. Inversely related to the square of the distance from the source. All right. So what that means is that as we increase our distance from a source, then the intensity of the radiation from where it was created goes down. Increased distance, intensity goes down. Intensity, again, is just going to be a measure of the number of X-ray photons, mass. If we're doing direct square law, be mass. And if we're doing the inverse square law, it's going to be a measure of radiation exposure, like milligray, something like that. Okay? So what that means is that if I'm standing 1 foot away from the fluoro table, that really should be where 100% of your radiation dose comes from, or pretty close to it. If I'm standing 1 foot away from the patient, then I can decrease my dose by taking a step away, right? Increase my distance and the amount of radiation I'm going to receive. The patient is your radiation emitter. So I step away from the patient, my radiation dose is going to go down. Okay. So let's work this and see how it works. So the inverse square law, intensity 1 over intensity 2 is equal to D2 over D1 squared. Okay, so intensity 1 over intensity 2 is equal to D2 over D1, and we're going to square this whole thing. Remember, I like to simplify things if I can, right? So let's say we've got a radiation exposure of 1, okay? So we're going to change our distance, but we don't know what that's going to result in. So 1 over x is equal to, let's say, our original distance, which is our D1. D1 is also 1. And then our new distance is going to be 2. So I'm standing 1 foot away from the patient. I'm getting 1 of something, MR, milligray, something. And I take 1 step back and I increase the amount of exposure, I increase my distance by a factor 2. I double my distance. I'm now 2 feet. This is the part you're gonna kind of trip over a couple of times. One, there's two parts. One is not making sure that you're doing inverse, okay? Make sure that it's I1 over I2 is equal to D2 over D1. But the other thing you're gonna miss is that little part right there. Okay, so the first thing you got to do, remember PEDMAS, is to get rid of the parentheses. So we're going to square this whole thing on the other side. So 2 times 2 is 4. 4 over 1 times 1 is 1. And that is 1 over x. So we cross multiply. 1 equals 4x. Now what do we do? Divide both sides by 4. I'm out of room. So what is x then? 4. Your radiation dose went down by a factor of 4 because you doubled your distance. Let's try this again. And this time, let's say my intensity, we'll leave intensity at 1. Now let's say my original distance was 2, and my new distance is 4. Okay, so what's the first thing we do? Square it. 16 over 4 is equal to 1 over x, because 4 times 4 is 16, 2 times 2 is 4. Now we'll cross multiply, and we have 4 equals 16x, divide both sides by 16. And what do you think we got? Bingo. I lost you. Or lose you.
1 over x equals 16 over 4. Like the step after that.
Yeah, we squared this. So 4 times 4 is 16, 2 times 2 is 4. Right? So this didn't change. It's still 1 over x.
So then what do we do after that?
You can't see, can you? After this, what we would do is cross multiply. So that would be 4 is equal to 16x. And then divide both sides by 16, and we come up with the same number. We can do this again for 3. We can do it again for 4. We can do it again for 5. We can do it again for 6. What do you suppose the answer is going to be every single time? It's going to be 1/4. Okay, it's called the inverse square law. Yeah, what is a law? It's reproducible. Nothing changes it. It's always the same. Okay, inverse square law. Every single time you double your distance, then the intensity is going to decrease by a factor of 4. Without fail. Every single time. So, do you need to work this ever again if you've got to double a distance? No, you don't. You don't. Okay. So, how do we use this? Well, we use this in calculation of dose and for your understanding of how to minimize your dose. So again, you're doing a fluoro procedure, you increase by even just 1 step and your dose drops dramatically. So a little is good, is a lot better.
Yeah.
Yeah. So what you don't want to do is you don't want to scare the patient to death. You don't want them, look like a weirdo, right? So you're not going to back all the way up to the wall and, hang out at the wall. So that the doctor asks, can you give them some barium? And you got to hike in to give them barium. You don't want to do that. But you can back up a couple of times. Also talked about this. Who else is working with you? Yeah, right. So there we go. Let's say this is the area that is being exposed by the patient. Okay? That's an entire exposure area. This is completely not what I intended to bring this for. All right? But let's say PA is working right there. You're, standing here, you're giving the patient barium, whatnot. Are you getting hit? I mean, here, this actually worked out great. Where am I getting hit? Where am I getting hit? Everywhere, right? So You know, you take a step back, am I still getting hit everywhere? Yeah, but I'm getting hit with a lot less, right? Now what happened?
You're not getting.
I'm not getting hit with some of that down there, right? So you don't have to get up and spoon, you know, the PA to reduce your dose. Just kind of get out of the line of sight. Anybody ever played paintball? Okay, a couple of people. All right. So playing paintball, that's a blast too. Airsoft's kind of taking it over. I never played airsoft, but I used to play paintball with my sons, and they were little. Nothing says loving like shooting your son with a 68 caliber semi-gelatinous ball traveling at 250 feet per second. So you don't have to be right up on something for it to give you cover, right? So let's say you've got a PA that you're working with that's a lot smaller than you. Okay, so X-rays don't bend around the PA, right? Don't bend around the radiologist. So if you've got somebody that's smaller than you, the X-rays are coming and they're kind of spreading out like that, right? They're hitting the PA, but some of them are coming around the PA like that. So I've got this going on right here. Am I getting hit? Step back away from the PA, and if it's still going at the same distance or same rate, am I getting hit now? The answer is no. So you're actually better off backing away from them a little bit, not making it weird, cuddling with them, right? So get behind them to a degree. You don't have to get right behind them, but get behind them to a degree so that you're not in line of sight of where the patient's being irradiated. And your radiation dose not only drops to that, it drops to almost nothing. Okay. And if you're working with a testy radiologist, like they don't make those, right? Or a PA that is, doesn't really appreciate you letting them take the bullet, you might, they might grumble at you, but again, we kind of walk through how much you're getting paid, right? What you're paid? Right. Not for another 2 years. So use them. Okay. So that's how we use inverse flow and time distance shielding, or at least distance shielding. So we've also got another law that looks a lot like that, and that is the direct square law, where we have mass 1 over mass 2 is equal to distance 1 over distance 2 squared. Okay, notice the second half of this is no longer inverted, right? So before, with the inverse square law, is d2 over d1. Now it's d1 over d2. So it's a direct square law. Mass 1, d1. Mass 2, d2. Okay? So since your radiation intensity drops by a factor of 4 if you double your distance, according to the inverse square law, what do you suppose you would have to do to compensate for distance changes in your technique for the patient? That's what mass is. Increase by a factor of? 4. Yeah. Increase by a factor of 4. It's the exact same thing, just with the opposite side flipped. Now here's where it gets sticky. Nothing can be easy, right? Nope. Nothing is ever easy. So what are your two distances?
1 and 2.
The two distances out of Merrill's, the two distances we use. Yeah. 40 and 80, right? So we have 40 inches and we've got 72 inches. Okay. So, and of course, if we flip this around, that would be the radiation dose as well. But since we're talking about exposure to the patient, that's what we're going to talk about here. All right. So let's say you make an exposure on a patient today with 1 mass, simplified, and you're using 40 inches today. The patient is sick, right? You did a chest X-ray on them. They couldn't even sit up. But tomorrow, be healed. They're feeling much better. So you can go back into the room and shoot with 72 inches tomorrow. Okay, so our new mass, we don't know. We used 40 inches. Now we're going to 72. So 40 squared would be 1,600. Why is it? I used to know this and I don't anymore. Because I'm getting old. Let's see. 72, 5,184. 5,184. All right. So what's your next step?
Cross multiply.
Cross multiply. So we have 5184 is equal to 1,600x. Now what do we do?
Divide by 16.
Divide by 1,600. So x is equal to 5184 divided by 1,600 is 3.24. Okay, what do we call this? The direct square.
Law.
We call it a law because it never changes. Right? So do you ever have to work out this for any, technique correction where you're going from 40 to 72 inches?
No.
No. The only thing you got to do is multiply by 3.24. Well, I got a lot of penguins on my iceberg. I can't remember 3.24. Can you remember 3.25? 3.25. That'll get you there. You're never going to have two answers on a test all the way through the registry that are going to be that close together with the answers. Even my tests, they're not going to be that close with the answers. So if you can't remember 3.24, just remember 3.25. Multiply by 3.25. So what if today you shot at 72 inches, the perfect x-ray, and they took a turn for the worse, and tomorrow you've got to shoot 40 inches? What would you do?
Divide by 3.24.
Divide by 3.24. Okay? For now, that's all you need to know. Double distance 4 times. 40 to 72, 3.24, or 3.25. Right?
So you're just trying to find your second mass.
You're trying to find your new mass with this distance change. Because of the inverse square law, we have to have a new technique, and that's what the direct square law tells us. What is our new technique? So this is kind of getting into next semester, but you can always tell the difference between which formula you need to use, because with if you need to use the direct square law, your question is going to ask you about new mass. You shot yesterday with 40 or at 40 inches with whatever technique. What is your new mass if you increase to 72 inches? All right, so that's going to be the direct square law. The inverse square law is radiation exposure was this much at this distance, and it's usually a short distance, 1 foot. What's it going to be at 2 feet? Measured in milligray, milliroentgens, something like that. Okay. So, but that's really next semester. So what do you need to know for this semester? Double distance 4 times, right? Right? Or if it's inverse square law, double distance, it's still a factor 4, but it's 1/4, right? 40, 72, 3.25. We'll get you there. Okay. So any questions on that? I don't want to see a whole lot of, I don't see y'all are OCD and you're gonna have to work this out. I get it, but I don't want to see the whole class doing this because this is just not necessary on the test. Not on this test. There'll come a time where this is gonna be necessary. It ain't this test. Okay? So just relax and remember, to make sure you go from 40 to 80 is factor of 4. 47 to is 3.24. Yep.
So what kind of question would you ask?
Pretty much what I described up here. You took a chest X-ray on a patient with one mass today at 40 inches. What would you, and they would be word problems. What would your new mass be if you increased your distance 72 inches? You multiply and, the direct square law is not in this chapter. I'm just, introducing this because we're going to get to a plus. This is the one you're going to use more. Right? I mean, you're actually going to use this if you shot an image today at 40 inches and then next week, same patient, 72 inches, you got to know how much to change your technique.
So is the direct going to be on the test along with the indirect?
No, just indirect.
Just,
Just indirect.
so on indirect, it would be like if you increase your distance from 2 feet to 4 feet, what is your,
It's not going to be mass. It's going to be exposure like MR or milligrade, something like that.
So like, once you do it, and then you like add or subtract to the technique you already used. Let me.
Okay, so it would just be straight division, actually. So, or, yeah, I mean, multiplication either way. So all right, let's do this one more time with inverse. I1 over I2 is D2 over D1 squared. So let's say, just to give one that, would actually have to finish out like that and not make it quite so simple. Let's say the patient received, this would be a big old dose, but 10 MR at whatever distance. Okay. So, we don't know what our new MR is going to be, but let's say our original distance was 1 foot and our new distance is 2 feet, just to keep it kind of simple. So again, make sure you square it. So it's going to be 4 over 1 is equal to 10 over x. So cross multiply would be 10 equals 4x. So divide both sides by 4. So that'd be 2.5. That'd be your entire answer. So your new dose then is 2.5. Yeah.
Okay.
No follow-up to that. It's a package deal. Yeah.
it's just in a word problem, so just,
Yeah. It's just in a word problem. So you just, pick it out and plug it in. Pick and plug. Okay. Any other questions? We're going to do this to death over Amy's going to get to it. I'm going to get to it next semester. We're going to hammer it in sophomore year. So, at this point, you just need to be familiarized with it. You're actually going to have to work it at some point, but that time is not now. I just want you to know the basics of it. Okay. Any other questions? Okay, so I'm going to leave this with you because I'm going to butcher this every single time. Well, matter and energy, conservation of matter, conservation of energy. We've talked about matter and energy on page 67, E equals MC squared, that whole thing. Conservation of energy just says that you can't create or destroy energy. You can just transform it. You can transform it from matter. And I think we talked about that in chapter 1. You cut down a tree, you burn the tree, you get energy off of it. So it's conversion, right? So we already talked about those things, but what I'm going to leave you with to work on your own, because I screw it up every single time, is no, that's not in this section. I'm sorry, and that's it. I thought temperature conversion was in this section, but that's electromagnetic spectrum again. Any other questions?
so we're gonna have to know like, Planck's equation.
Planck's equation, I think that as far as working it, no, still no math, no real math,
Yeah.
But from the perspective of what Planck's equation introduces, that being energy into the wave equation, yeah, just kind of definition of it. All right, do y'all have a test ready? Randy?
And then
Correct.
patient care.
You got a patient care test? Okay, do y'all want to put this off until next Wednesday? Please. Okay, then we'll put it off until next Wednesday. We'll pick up with the first part, chapter 5 on Friday.